So we're going to try to get through an entire unit of study in this lecture. It is probably going to be run a little bit long, but we seem to do that when in the last unit or the last lecture we covered an entire unit of study, that of aldehydes and ketones, and now we're going to move into a couple of other carbonyl containing functional groups, look at them in more detail. The two we're going to be looking at are carboxylic acids and esters. We will start by looking at carboxylic acids and then move into esters. We're going to find they're very structurally related, so the segue between the two functional groups should be fairly straightforward. Now, a carboxylic acid, by definition, we see that this group right here, it has a particular name of a carboxylic acid, and that's based upon these structural motifs which it bears. We'll notice that that there's two pieces in there. That C double bond O is a carbonyl, and the OH is a hydroxyl. Thus, when we express the name of the functional group, just like the name of an alcohol functional group is a hydroxyl, say, the name of the actual functional group on a carboxylic acid is considered a carboxyl. It's sort of a contraction between carb for carbonyl and oxyl with hydroxyl. So that's the carboxyl group on the carboxylic acid. Carboxylic acids can be written in any number of ways. We saw over here on the left, the hydroxyl was shown as O covalent bond H. Well, we can contract that somewhat, and we can have something like we see up top here, where that covalent bond between the oxygen and the hydrogen on the carboxyl group is just sort of condensed. So we can see it both ways. Most of the time it's condensed, just like on an alcohol functional group. The hydroxyl is condensed as just OH and not O bond H, but either are fine. There's a couple of different ways of a condensed view of a carboxylic acid. We see these sometimes. We could have COOH or CO2H as condensed versions of a carboxyl group. And I'm just showing you this because they may be, you may see these more often in the literature or in biochemistry and that sort of thing. There's, rest assured, there's a number of different ways of expressing the carboxyl group. So its basic structure is, we find that it's yet another one of these carbonyl containing functional groups. There are 5 of them that were in our original 13, and that carbonyl, as we saw before, has 2 legs poking out on it, 2 covalent bonds. Because of that rule of 4 for carbon, there's 2 more bonds on that carbon, and it's all about what flanks that carbonyl, which defines the functional group. With a carboxylic acid, we're flanked on one side by a hydrocarbon type carbon, and on the other side by a hydroxyl group. If we have this showing up, it is by definition a carboxylic acid or a carboxyl group. Again, here's some just general representations of that. Here's a carboxylic acid showing the carboxyl group sort of in almost full form, and the next couple of carboxylic acid molecules show that carboxyl in one of those contracted forms or condensed forms, CO2H or COOH. So we have been going through each of these functional groups and talking about the intermolecular forces which define them. How strongly are the molecules of, say, a carboxylic acid, how strongly are they held together compared with an ether or an aldehyde or something like that? And we found that with, as before, similarly massed molecules, the stronger the intermolecular force between that molecule containing a particular functional group, the stronger that intermolecular force, the higher the boiling point. So we're just going to add to our listing that we've seen thus far. And the first one, of course, was an alkane, which had the weakest intermolecular force, that of dispersion forces, boiling point about 0 degrees Celsius. Our ether, which had a stronger intermolecular force, not much stronger, but it's still stronger. That weak dipole-dipole force gives that particular ether about an 8-degree boiling point. Notice all of these molecules that I'm going to be showing you have about the same molar mass. So that is specified. So any difference in boiling point is attributable to increases in the strength of intermolecular forces. We then move to either aldehydes and ketones. They're sort of in the same bracket, if you will, and they both have strong dipole-dipole forces. We don't discern between aldehyde or ketone being always boiling higher than an aldehyde or something like that. They're held within their own sort of bracket together. So they have the strong dipole-dipole force, and in this case, their boiling points are about 50 degrees Celsius or therein. Up to this point, our alcohol has been the king of the hill, if you will, bearing hydrogen bonding, the strongest intermolecular force. Now, in this case, has a boiling point of about 100 degrees Celsius, that strongest intermolecular force. Well, that king is about to get knocked off its hill, if you will. We now bring in a carboxylic acid of similar mass. Look at that boiling point. It's about 120 degrees, so it's higher than that of the alcohol. Now, why might that be? And it's because of the basic structure of that carboxyl group. We have the strong dipole-dipole force from a carbonyl group and the hydrogen bonding from a hydroxyl. So we have two strong intermolecular forces acting together, and that knocks the alcohol off its previous perch as the traditionally, so far that we've looked at, that highest boiler, if you will. Now a carboxylic acid bearing two strong intermolecular forces tips that scale towards itself. Maybe we're noticing a little bit of a pattern here. When we get out of physical properties, boiling points of many functional groups, we've barreled directly into nomenclature. Carboxylic acids are no exception. We'll be looking at UPack, carboxylic acid nomenclature. UPack, if you remember, was that rule-based nomenclature that we've become familiar with. Even between different functional groups, there's always a similarity, a strong similarity between them, because it's the same sort of rules over and over, with thrown in quirks that are specific for the particular functional group that we are looking at. So in this case, UPack nomenclature of carboxylic acids, we always start the same way, looking for that parent structure. In this case, the longest continuous carbon chain containing that carbonyl carbon. And if we're approaching this molecule over on the right here, we find that the longest continuous carbon chain is this 6-carbon chain that we see here in red. If this were a 6-carbon alkane, it would be hexane, but it's not. We recognize that as a carboxylic acid and not an alkane. So thus, we will remove the E from the corresponding alkane name and replace it with the mouthful oic acid. Hexane becomes hexanoic acid. Now, just like aldehydes, notice where the carbonyl group must always exist on a parent chain in a carboxylic acid. By structural definition, it must exist at the very end carbon. We saw that with aldehydes too. They had to, that aldehyde carbonyl had to, by structural definition, exist on an end carbon. Same with a carboxylic acid. So we're going to have to number this parent chain now, giving that one designation to the carbonyl carbon, but not mentioning it in the name, because it's always one and thus redundant. So we would number this parent chain in this fashion, giving that one designation to that carbonyl of the carboxyl group, always. Having done that, we've given an address to the only substituent on there, and we name and number these substituents using the standard UPack protocol done previously? Well, that is a bromo group, and that bromo group happens to live at the 3 carbons. So we would lasso in here 3-bromo hexanoic acid would be the name of this structure. Okay, let's ply our trade here. Having worked on a more elementary molecule on the previous slide, we have some more complex problems for carboxylic acid nomenclature in front of us. Let's take a look at the structure over on the left. We see that it is, without question, a carboxylic acid. So we are going to be naming it as such. And the first thing to do is to find the longest continuous carbon chain. And might have to try a number of different ones, but we find that this 8-carbon chain right here. It meanders around, and we might have to look at these and try different paths, but we find that this 8-carbon chain. If this were an 8-carbon alkane, it would be octane, but it's not. It's a carboxylic acid. So we remove the E from the corresponding alkane name and bring in oic acid. Now we have to number this chain such that the carbonyl carbon always gets the 1 designation. So we're going to number it in this fashion, 1 through 8. And now we're going to look at what our substituents are. I see a couple of methyl groups right there and an ethyl group right here. Now, E in ethyl comes before M in dimethyl. So we're going to start with the ethyl. That lives at the 5 carbon, as we can see. So we're going to start with 5-ethyl. Then we go back and look at our two methyl groups. They are connected to the 3 and the 6 carbon, respectively. And we're going to bring this in as 3,6-dimethyl. So 5-ethyl, 3,6-dimethyl octanoic acid. Quite a mouthful. And so again, sometimes you wonder, how did I possibly do that? It's just so long and complex. Well, it's because we break it up into manageable chunks and we follow the rules one step at a time, and it fits itself together. Let's look at the center molecule right here. Again, we see that this has a carboxyl group, so we're going to be naming this as a carboxylic acid. Longest continuous carbon chain would be this one, trying all possible routes. This 7-carbon chain right here, if this were a 7-carbon alkane, it would be heptane. But it's not. It's a carboxylic acid. Does this get repetitive? Yes, it does, but repetitive is good here. So it's not an alkane, it's a carboxylic acid, so we're going to remove the E from the corresponding alkane name and bring in oic acid. Next, we'll number this, giving the 1 designation to the carbonyl of the carboxyl group, 1 through 7. And now we identify our substituents. Here at the 3 carbon, we have a fluoro group, and here at the 4 carbon, we have an ethyl group. Now, E in ethyl comes before F in fluoro, so we start this, that 4-ethyl, and the fluoro at the 3 position, 3-fluoro. 4-ethyl, 3-fluoro heptanoic acid. Lastly, over on the right, again, sometimes we're given a name and we're asked for a structure. And to do that, we look towards the end of the molecule. I see pentane here. Pent is 5. So I am going to draw 5 carbons in a row and number them in any direction I like. I'll start from the left and go to the right. And I see oic acid here. That means there has to be a carboxyl group at that 1 carbon. So I'm just going to draw that in. And now we look towards the front of the molecule and we see 3,3-diethyl. So there's 2 ethyl groups and they're both at that 3 position. So we draw them in. And that is the end. So again, these name going to structures are typically much more straightforward than the other way around, but both are eminently doable using this UPack nomenclature. Sort of an anomaly in the UPack nomenclature of carboxylic acids is the nomenclature of cyclic carboxylic acids here where we have a cycle and attached to it is a carboxyl group. Now, if we have this going on, one might think, using the UPack nomenclature we had looked at before, that this would be cyclopentanoic acid. Why cyclopentanoic acid? Because that is 5 carbons, that's cyclopentane, and we have a carboxylic acid, so cyclopentanoic acid. That is actually not the case. The proper name is a mouthful. It is, we name the entire parent structure here first, cyclopentane, and then we move to the carboxyl group, carboxylic acid. Cyclopentane, carboxylic acid, not cyclopentanoic acid. So just keep that in mind. Let's look at an example as we move forward here. Here's a carboxylic acid connected to a cyclic structure with some other substituents connected to it. Well, we see that our main piece right here is this 6-membered ring, cyclohexane, with the carboxylic acid connected to it. So this would be, over towards the end, cyclohexane carboxylic acid. But we have a couple of bromo groups on there. So we now, on cyclic structures, in this case, we have to number the ring. But in this case, that parent structure, having that carboxyl group there, that's always the 1 carbon on that ring, is the one containing that carboxyl group. So we put the 1 there. And as before, we count around the ring in the direction which brings the substituent or the substituents into the lowest numerical designation. I hope you would recognize that to have to count around counterclockwise to do that. And I bring in our bromo groups at the 3 and the 4 position. Thus, I can front load this molecular name as 3,4-dibromo cyclohexane carboxylic acid. Again, quite a mouthful. So predictably, once we're done with nomenclature, we're moving into reactions of a particular functional group. In this case, we'll be looking at a couple of reactions of carboxylic acids. The first one derives from what we see here is in the name of the functional group. We have an acid. If it's a carboxylic acid, it must be acidic, and thus it can undergo an acid-base reaction. It acts as the acid in that acid-base reaction. So an acid-base reaction is always a pair. Our carboxylic acid, which we see here, must be paired with a base. In this case, it is a strong base, typically a hydroxide salt, such as sodium hydroxide, potassium hydroxide, and the like, but it must be one of these strong bases. And let's see what is cleaved out of here. Well, look over on the product profile on the right, we see that water is a side product. HOH, well, where does that HOH come from in the reactant profile over on the left? Well, I see H right here, OH right there. So that's the water that gets cleaved out of this. But what is left? Well, everything but the HOH. And look over on the product profile. The resulting product is known as a carboxylate salt. What was a carboxylic acid is now a carboxylate. So in an acid-base reaction, the hydroxide, OH-, removes an H+ hydrogen ion from the carboxylic acid. So we have to be, in the product, having lost an H, but we also have lost a positive charge, H+, remember? So what results must be that O-. That is considered a carboxylate. And when it is shown with its counter ion, in this case sodium, Na+, it is known as a carboxylate salt. So let's see if we can look at some examples of reactions of carboxylic acids playing our favorite game that we have, What's in the Box? So here's a couple of examples, example problems. Here we have, and just pretend it doesn't say acid-base reaction there, but we would sleuth this out. This is a carboxylic acid. This is a strong base. this is an acid-base reaction. And we see over on the right-hand side that water is cleaved out of this. Well, what's left? Well, the H would be gone from the carboxylic acid, and the OH would be gone from the strong base, and what's left? Other than their respective charges, we can just put that right over into the box, O minus K plus, because we know it's going to be a carboxylate salt in there. Now the one on the bottom, our box now is part of our reactant profile, but let's again sleuth this out. We have our box right here, plus a strong base gives a carboxylate salt plus water. So in this case, all of those together signifies an acid-base reaction. So what is that reactant that reacts with the base? Well, it is everything we see here in this carboxylate with a hydrogen. Instead of O minus, it's going to be an OH. That's what we can pull out of this. Nothing fancy there. It's simply that original carboxylic acid. Another reaction involving carboxylic acids is what is called an esterification reaction. Esterification, which should give some hint as to what we're actually synthesizing in this case. This is a functional group condensation. Remember in the last unit, we saw the functional group condensation of an aldehyde and an alcohol condenses. A covalent attachment between them to form an acetal or hemiacetal, and we looked at that. This uses some perhaps more familiar types of products. In this case, we have the condensation between a carboxylic acid and an alcohol under catalytic acidic conditions, which gives another functional group which we're familiar with, an ester. An ester functional group, and it spits out water as a byproduct, so that we can actually look at this now, and I've somewhat color-coded this such that so again, if we start to look at what is one of the products, the side product is water, HOH. Well, where can we take HOH from? Well, let's take a hydrogen from H from the carboxylic acid and an OH from the alcohol. And what is left? They must be connected together. And if we look over on the other side, we have indeed connected what was left on that side together, and that is diagnostic ester connectivity. A carbonyl flanked on one side by hydrocarbon-carbon, flanked on the other side by an oxygen, which is in itself connected to or bonded to a hydrocarbon-carbon. Diagnostic ester linkage. Sort of going back a little bit now, but that is definitely an ester, so that anytime we have these conditions of catalytic acid and heat, and we have a carboxylic acid and an alcohol in the same reaction vessel, we're going to be getting an ester functional group, that functional group condensation. So let's look at a couple of examples. Again, playing what's in the box here. Here, let's look at the one on the top, an esterification reaction. We would have to recognize it as such. Well, let's see. I have a carboxylic acid and an alcohol under conditions of catalytic acid and heat. Oh, that was an esterification reaction. Let's see if we can flesh this out a little more. It spits out water. That's HOH. Well, let me erase from here, or black out, the HOH from our reactant profile, and what exactly do we get if those are blanked out? Well, we just connect them, and that connection would be that ester. We have our 2-carbon part of our alcohol right here, and that connects with that original carboxylic acid fragment to give what we see in the box right here, that ester structure. Looking down on the bottom, we've moved slightly our box, if you will. Here we have a carboxylic acid over on the left-hand side, plus something under conditions of catalytic acid and heat gives an ester plus water. So in this case, we remember what are the components that go into forming an ester. Well, that's a carboxylic acid and an alcohol. I have my carboxylic acid over here, so what's in the box must be an alcohol, OH. Well, what structure of our alcohol? Interestingly, now we have to look at our ester and be able to derive from that ester what was that carboxylic acid component and what was that alcohol component. And the cut, if you will, is right through that bond right there. Right through that bond. Over on the one side, this is our carboxylic acid component, the one containing the carbonyl. And on the right side, the way I've drawn it, this must always be our alcohol component. Look at what I have. I have a phenyl group with an O. So all I have to do is add an H to that O, and that is going to be the alcohol which goes into this particular esterification reaction. So it is important when we look at an ester to be able to cleave out, discern what component of that ester is derived from the alcohol and what is derived from the carboxylic acid. Let's look at the answer on the top example here. So we would say that if we had this dotted line always through this bond on an ester, that this component over here was derived from the carboxylic acid. And we can see that is indeed the case. The architecture is identical. And while on the other side, this component was derived from the alcohol, and we can see from the architecture of that alcohol that that is indeed the case. So always that's going to be able to discern that from an ester, breaking it down into its respective components. If we need to discern, well, what was that carboxylic acid that went into that structure? What was that alcohol that went into that structure, which was the basis of the problem on the bottom of the slide here. So since we just synthesized an ester from a carboxylic acid and an alcohol, this would be a good time to seg into a study or a general idea of the physical properties and attributes and salient features of esters. Our physical properties of esters, now we see remember when we think of physical properties, we think of boiling points in comparison to other similarly massed molecules bearing different functional groups. Well, it turns out that the boiling points of esters are similar to those of aldehydes and ketones of similar mass. Because since esters, if we look at the structure over on the right-hand side, there's an ester. Esters cannot hydrogen bond. Right here we have an O carbon bond. We have to have an OH bond in order for it to hydrogen bond like carboxylic acids. Well, we don't have that. All we have is that carbonyl, which has a strong dipole-dipole forces. So esters have strong dipole-dipole forces similar to those that we saw, or identical to those that we saw in representative ketones or representative aldehydes. Thus, we can say that their boiling points, the boiling points of esters, are similar to those of aldehydes and ketones of similar mass, because of we have our similar predominant intermolecular force of strong dipole-dipole forces. Now, interestingly, if we notice, remember when we looked at thiols, those SH molecules, we said one of our salient features of these, our physical properties, is they're stinky. They smell bad. So we finally got out of that trope of always looking at boiling points, and sometimes they have some other interesting properties. Well, esters have some interesting sort of olfactory properties as well. The esters typically have pleasant aromas. Most of the time they're fruity type of aromas, frequently used in artificial flavoring. And what we see is that certain esters have scents or flavors like certain fruits. Indeed, this particular ester over here on the left-hand side has the smell of raspberries. That's because raspberries naturally produce this ester and many other ones. So it is sort of a no-brainer for people to say, like, well, if I wanted some artificial raspberry flavor, maybe I should just dump in some of this ester. And indeed, that is artificial raspberry flavoring, that particular ester that we see right there. Esters are very easily worked out of our system when we ingest them, so that they're not considered poisonous. Their residence time, if they're ingested, is very short, and they're excreted, so they're frequently used in artificial flavoring. Let's look at the middle one, that ester that we see in the center right there. Well, that smells like apples, and it tastes like apples. Indeed, apples naturally produce this particular ester. So if we were looking for some fake apple flavoring or something like that, this particular ester would be the go-to. So you see where this is going. Look at the ester over on the right-hand side. This ester right here, well, that smells like bananas. And indeed, bananas produce naturally some of this ester, which gives it its diagnostic flavor and smell. But for artificial banana flavor, guess what? If anything I want to have artificial banana flavor, I'm going to throw in some of this ester in order to give it that artificial banana flavor. So let's take a look at some ester nomenclature. Ester nomenclature departs a little bit from the standard nomenclature we've used at UPack, that rule-based nomenclature, just because it is the conglomeration, if you will, between two functional groups. It's the first functional group that we've named that is the result of the functional group condensation. There is some similarities to UPack nomenclature, and there are some differences. Since esters form from the condensation of both a carboxylic acid and an alcohol, it is always, an ester name is always two words, one of which reflects the alcohol portion and one of which reflects the carboxylic acid portion of that ester, which is ultimately being made. So here is an ester condensation reaction from a carboxylic acid and an alcohol, and I have labeled the names of the carboxylic acid and the alcohol. So the first word of the two in an ester nomenclature is always the alkyl group of the alcohol component. Well, what does that mean? What is that carbon architecture contained connected to the alcohol? Well, here's the alcohol, and I see two carbons. Therefore, it's ethanol. So, but that specific alkyl group is ethyl. So ethyl would be that name, and that ethyl is put first over on the name of the ester. So we started it out. The first word is ethyl. The second word is that this is where we go back to UPack a little bit, and we have to look at the carboxylic acid sort of closely. Well, how many carbons in this carboxylic acid? Way over here on the left, I see 1, 2, 3. And indeed, this is known as that's 3, propanoic acid. Propanoic acid. If it were a 3-carbon alkane, it would be propane. But it's not. It's ultimately going to be making an ester, so we have to add the suffix O8 after removing the E from the corresponding alkane name. Propane becomes propanoate. Ethyl, propanoate. So again, yet another suffix that we have to learn. We use these sort of augmented UPack, quasi-UPack rules when naming esters moving forward. So let's take a look at some examples. I've listed up on top how we're going to be doing each of these. First word, alkyl group of the alcohol component. Second word, removing the E from corresponding alkane name, putting in O8, just so we have something to work with. Anyway, I have 3 examples here. Let's look at the example over on the left. So what do we do first? We have to find the alkyl group of the alcohol component, but what is the alcohol component? We have to be able to separate that ester into the alcohol component and the carboxylic acid component. So to do that, like we did before, we see that we break through that particular bond. We see in red there, I've labeled as that's the alcohol portion. The other part, including the carbonyl, is the carboxylic acid portion. With the alcohol portion, what is that alkyl group on there? Just that carbon group. We find that is an isopropyl group. Remember that isopropyl, 3 carbons connected in the middle? And that's our first word. So we're going to put that down there. Next, so it says remove the E from the corresponding alkane name of the carboxylic acid component. Well, how many carbons are in that? Well, there's 1, 2, 3, 4, 5 carbons in there. So that would be pentane. It's not pentane. It is an ester. So that second word, we put down pentane to start, but we remove that E and bring in the suffix O8. Isopropyl pentanoate for this structure. Let's look at the middle structure. Again, we have to separate this into the carboxylic acid portion and the alcohol portion. Again, through that diagnostic bond that we see here, always on an ester. And we're going to start, our first word is going to be the alkyl group from the alcohol component. Well, that's a phenyl. That's phenyl. So that is indeed our first word. Next would be, what is that carboxylic acid portion? How many carbons are in there? Well, let's look at that carboxylic acid portion. I see 1, I see 2. 2 carbons. So a 2-carbon alkane would be ethane, or ethane ... We'll put that down here, ethane, but we see that this is an ester. So we're going to recruit in the suffix, instead of E, ethanoate. Phenyl ethanoate. Fair enough. Let's now go over on the right. Now we have a name, we need a structure. The name is butyl octanoate. Well, that's diagnostic nomenclature for an ester. So I am going to just draw an ester bow right there with 2 sticks coming out of it, and I'm going to be adding the correct number of carbons into there. On that alcohol component, it's going to be 4 carbons. Why? Because it says butyl. But is 4. Remember, that cut between the carboxylic acid and the alcohol component is through that bond with the alcohol component over on this side. So I need 4 carbons over on that side. There they are. 1, 2, 3, 4. Always good to count your carbons. It may seem like a rookie thing to do, but it is so easy to draw an extra carbon or drop a carbon. Count your carbons, ends and the bends, and you won't make that mistake. Well, then that means on the other side of that dotted line is our carboxylic acid portion, and that we have octanoate. Octanoate. Oct is 8. So on the carboxylic acid portion, including that carbonyl carbon, I'm going to put 8 carbons. So that's 1 carbon, and I draw in another 8. So 2, 3, 4, 5, 6, 7, 8. I know I sound like a rookie, but it is important. So just so you don't make that mistake of adding in 1 extra carbon or too many carbons. So that would be the proper structure of butyl octanoate. Would like to take a brief interlude here while still staying on the subject of esters, but I'd like to start looking at another type of polymer. Remember back in this Unit 2, we were talking about polymers, specifically addition polymers of alkenes. This is a different type of polymer, although polymers always have the same idea. It is a very large molecule structured from repeating units, these that are called monomers. Now, in the case of our addition polymers back in Unit 2, it was one type of monomer, one type of alkene, just connecting and connecting and connecting over and over and over together. In condensation polymers, we have 2 monomer building blocks, two of them. And what we're going to be using, there's many different types of condensation polymers. Since we're talking about esters, we're going to be talking about, and probably a word you're very familiar with, this concept of polyesters. Polyester, like many uses of polyester polymer, notably in clothing, polyesters, which means that we have a polymer of esters. So esters are built from the condensation of a carboxylic acid and an alcohol. Well, let's look now at what our building blocks would have to be on a polyester. There's some variation, but typically one of our monomers is a dicarboxylic acid. A dicarboxylic acid, and another is a dialcohol, meaning we have a molecule which has two carboxyl groups on it, a dicarboxylic acid, and a molecule with two hydroxyl groups on it, that dialcohol. And we can set these up, if you will, in sort of a line. And basically all this would entail would be taking, equimolar amounts of our dicarboxylic acid and our dialcohol and mixing them together. And notice that if we mix these together under conditions of catalytic acid and heat, well, here's a carboxylic acid and an alcohol. Here's an alcohol and a carboxylic acid and an alcohol, which under these conditions can very easily condense, and that is exactly what happens. Notice I'm only showing two molecules each of the dicarboxylic acid and the dialcohol. Think, trillions of them, or quadrillions, or a mole of each, or something like that, but this is just to keep it on one page. What would happen under catalytic acidic conditions and heat? Well, we would form ester bonds between these. Notice the way I've drawn this is I've drawn these brackets with a little n right there, and that n is a very, very, very large number. So you can imagine this one strand going off on either direction into infinity, but indeed we have our ester bonds that we showed above sort of built into here. Of course, in each case, we would be spitting out water. Water would come out because water is a result of this. That would just end up in the reaction vessel. But we've formed a polyester. Now, again, polyesters we're familiar with in clothing materials. They have many other types of application depending on what the structure of the dicarboxylic acid and the dialcohol are. I've given you one example of a dicarboxylic acid and one example of a dialcohol. If we change up the architecture of the dicarboxylic acid and the dialcohol, well, the resulting polymer would have different attributes than the previous one. And these attributes can be tuned and they can be analyzed, and the different polyesters can be used for different applications based upon their attributes. So a particular organic chemistry problem that we could put towards this. Well, how about this one? Which of the following pairs of molecules could act as monomers in a polyester forming reaction? Well, by definition, we must have a dicarboxylic acid and a dialcohol. Do we have that in each case? Well, in this first case, I see a dicarboxylic acid and a dialcohol. So this would indeed be able to, these would be able to act as monomers in a polyester forming reaction. Next one, here's an alcohol, but this isn't a carboxylic acid. This is actually an example of an amide, a diamide. So it doesn't matter. This would not be able to react together as monomers in a polyester forming reaction. You see where I'm going with this. Let's look at the next one. Well, there's a dicarboxylic acid, a dialcohol, check. That would work as monomers in a polyester forming reaction. Well, there's a dialcohol, but this is a diamide, and I don't know why I'm putting an amide in there, but the point is we have to have a dicarboxylic acid and a dialcohol, or else no go on this. So in this case, that's how we would approach this particular problem from the standpoint of what do our two monomers need to look like. So let's get back to standard esters. Remember our formation of an ester. That was a condensation, functional group condensation of a carboxylic acid and an alcohol under catalytic acidic conditions and heat to form that ester and spit out water as a byproduct. Again, we're going to get into the idea of a reversal of a reaction. What if we had the reverse reaction? What if we had our ester and water, and could we go back the other way to reform or to form a carboxylic acid and an alcohol? Indeed we can. As before, virtually all organic reactions, if given the right conditions and reagents, we can send them back the other way. And this reaction, since a reaction going forward produced water, it was sort of like it produces water. It was sort of a dehydration reaction. Well, what would we call the reverse reaction? In this case, it is known as a hydrolysis. Hydrolysis. So we are using hydro for water. There's water, and we're going to be using that water on an ester. Hydrolysis of an ester. What does hydrolysis mean? Well, lysis means to cut something, to break something apart, to lyse something. So we're essentially using water, hydro, to lyse, to break apart an ester. And indeed we do. That one molecule breaks apart and we form two other structures. We've lysed that ester. We've broken it apart into a carboxylic acid and an alcohol. So the hydrolysis of an ester comes in essentially two flavors. So the first one is an acid catalyzed hydrolysis of an ester, which means we have acid hydrolysis. So in this case, it really is that specific reverse of the reaction we saw before. It is an ester. And in this case, to that ester, we add a bunch of water as a reagent under catalytic acidic conditions, and that is going to reform. We're going to use water, hydro, to lyse that ester, hydrolysis, to form our carboxylic acid and an alcohol. We've broken apart that ester. So we've literally, at least in the acid catalyzed hydrolysis of an ester, we've turned that around. We've literally turned it around. Even the same reaction conditions of the formation of an ester, they're the same for the hydrolysis of an ester. So we can look at, there's another type of hydrolysis of an ester, and if we're looking at this one as an acid catalyzed hydrolysis of an ester, the next one would be a base catalyzed hydrolysis of an ester. The base catalyzed hydrolysis of an ester is also colloquially known as a saponification. For whatever reason, saponification is a term sort of lost to the ages, but it has endured. When we hydrolyze an ester, only the base catalyzed hydrolysis is known as a saponification. And let's look at what the base catalyzed hydrolysis of an ester actually is. In this case, we have an ester, and we treat it with one of our hydroxide salts, our strong bases. In this case, only heat is required for conditions, and we end up with, remember the acid catalyzed hydrolysis, we ended up with a carboxylic acid and an alcohol. In this case, we do the same. We end up with an alcohol, and we initially end up with a carboxylic acid. But what happens to a carboxylic acid in an environment of strong base? Well, that was our acid-base reaction we looked at a few slides back. We form a carboxylate salt. So initially that, let me clean this up a little bit here for us. Initially that hydrolysis of an ester did indeed form our product profile, carboxylic acid and an alcohol, except that because we're under basic conditions, we have residual base, which converts that carboxylic acid into a carboxylate salt. So that's an important. Okay, sorry, I think you got cut off a little bit on the very end of that last slide, the last word or so. But let's look at some reactions of esters, specifically this hydrolysis of an ester, playing what's in the box. Well, let's see what we got here. Something plus water under catalytic acidic conditions and heat give a carboxylic acid and an alcohol. All of this information should tell us that we have all of the pieces together for the hydrolysis of an ester, specifically the acid catalyzed hydrolysis of an ester. So what are we ultimately going to do here? So if we look at our product profile, there's our carboxylic acid and there's our ester. We're going to make an ester bow in the box there, and we're going to attach to the alcohol component of it this alkyl group, and the carboxylic acid component of it would be this structure. Always that is the case, so we end up with this ester as the initial product, reactant in that reaction. We can tune it. We can actually go and look at that product profile, draw at the start of an ester, and decorate in the architecture on either side of that ester nucleus based upon the carbon architecture of that product profile. So let's look at the example down below. The one down below, we start with an ester with a hydroxide salt, strong base under heat, and we end up with something plus an alcohol. All of those criteria together should tell us that is the base catalyzed hydrolysis of an ester, and we know we produce an alcohol, but what do we have in the box here? This would be the carboxylic acid portion. Be careful not to draw in a carboxylic acid, remember, because this is base catalyzed and we have sodium hydroxide residual in there, so that carboxylic acid is going to become a carboxylate salt based upon what structure? Well, here is that carboxylic acid component, and that is what ends up as our carboxylate salt in the box that we see over on the product profile. So let's take another brief interlude, shall we? And we'll use this time to talk about an application of the base catalyzed hydrolysis of an ester. And we're going to use the same chemistry we've been discussing in the formation of something very practical, that of soap. Soap is the result of the saponification, the base catalyzed hydrolysis of a particular type of ester. Not a traditional ester, but indeed a type of ester linkage that we're going to be looking at in more detail in the second portion of the course, that of biochemistry. I'd like to introduce a type of ester here, or pre-introduce it, known as a triglyceride. A triglyceride is essentially a triester. And if we look over here, what I see is I have an alcohol, a tri-alcohol component, and 3 carboxylic acids. 1, 2, 3. 3 carboxylic acid components. It's called a triglyceride, but the important thing here is that they are connected by ester linkages. Those 3 ester linkages are indeed contained on one molecule, but as I clean this up a little bit here, let's imagine what would happen to this if I treated this with a strong base, sodium hydroxide, and heat. Well, I have over here on the left a bunch of ester linkages, and over here I have just the ticket to cause the base catalyzed hydrolysis of an ester, which forms an alcohol and a carboxylate salt. Well, let's see what would happen. What I guess is going to happen is we're going to cleave Remember, hydrolysis, we're lysing right there on all three of those esters to give a very interesting product profile. Let's look over on the left for just a moment. What do we have over here on our product profile? Well, it's this piece right here. That is a trialcohol, all one molecule with 3 hydroxyl groups on it, a very important biological molecule known as glycerol. Glycerol. And what do we have over on the other side after this base-catalyzed hydrolysis? Well, we formed the alcohol, but now we have to show our carboxylate salts. We indeed make 3 of them. Carboxylate salts, which we see right there. These are known as fatty acid carboxylates. Okay, they're carboxylate salts, but they're derived from what are called fatty acids. They're long-chain carboxylic acids. We can see they're very long carbon chains on these triglycerides. So that's considered fatty acid carboxylates once they have been sort of exposed or broken off from that glycerol. Fatty acid carboxylates shown here are essentially what soap is. This is what soap is. And we're going to talk about the action of soap and really answering the question, if I'm coming in from outside and I've maybe changed the oil on my car, or I've been digging in the garden and I have a lot of dirt and oil on my hands, if I just pass and wipe my dirty hands under a faucet just with water, with no soap, it'll get some of the dirt and oil off, but a lot of it's going to remain. However, if I wash my hands under the faucet and I use soap as well, and then I rinse off my hands, most of that dirt and oil, if not all of it, will be gone. So what is it about soap that can shuttle away, can remove dirt and oil so well, whereas regular water might not be able to? Well, let's take a look at that. Here is one of our fatty acid carboxylates that we see right here. And I am here to tell you that this is a very confused molecule when in an aqueous environment. If I were to throw this molecule into water, that's what an aqueous environment is, I'm going to have a portion of it which really enjoys associating with that water. That's this portion right here. Why? Because we have charges on it. Charged particles love to be in association with water. Whereas the other portion of this molecule can't stand being associated with water. Remember that like dissolves like? Well, this is all hydrocarbon over here on the left-hand side. That does not enjoy being associated with water, so it would try to get as far away from the water as it can. But unfortunately, those two pieces of the molecule are covalently bound together. So we can say on that one molecule that we have two portions. A hydrophilic portion, which means water-loving over here, and a hydrophobic portion, which means water-hating over there. Much of the time, since we're dealing with a lot of these things, which soap isn't just one fatty acid carboxylate, it is an uncountable number of them, we resort to the level of the cartoon. A cartoon to show this fatty acid carboxylate, because it's kind of a complex structure. What we like to do is show it written like this. The hydrophilic portion is typically drawn as a sphere, which we show right here, and the hydrophobic portion, that long chain alkane, is typically given as a sort of a squiggly tail over here. We still have that hydrophilic portion, the hydrophobic portion, but what ultimately happens, a whole bunch of these fatty acid carboxylates are getting together and saying, all right, how can we all get together in an aqueous environment and have our hydrophilic portions associating with water and our hydrophobic portions not touching water at all? Well, what happens is we form a micelle. A micelle is where we get a lot of these fatty acid carboxylates, and they associate themselves into a sphere with their tails pointed inward inside that sphere, which excludes water, and it's just these hydrocarbons associating together, which suits them just fine. They don't like water. While on the surface of this sphere, notice this is a cut through, we have all of these charged components which really love associating with the water, which we see all around. Notice that this is a cut through, sort of a cut through the sphere. Now, getting back to the dirt on my hands after changing the oil on my car or digging in my garden, dirt and oil have a lot of hydrocarbon to them, particularly oils and grease and that sort of thing. And hydrocarbons being, or grease being hydrocarbon, loves to associate with the hydrocarbon tails inside that micelle in such a way that a lot of the oil and dirt associates, here's that oil at the dirt at the center of that micelle, loves associating with those fatty acid tails because like dissolves like. Hydrocarbon likes associating with hydrocarbon. However, that is all contained within a sphere, and the surface of the sphere is all charged out here. So that means that this entire sphere, which is called a micelle, by the way, dissolves in water with its dirt and oil cargo. It dissolves in the water and flows away. By itself, dirt and oil, being hydrocarbon-like, has a very difficult time dissolving in just simply tap water and thus stays on your hands. When we use soap, we form an uncountable number of these micelles which shuttle away this oil and dirt in the dissolved state, because this entire micelle is dissolved into water and is then flushed away down the drain using the water coming out of the faucet. This is sort of a crude drawing. A much better artistic representation of this might be what we see right here, where the blue around it would be the water, and sort of these purple spheres on the outside would be the charged particles, and the not the charged particles, but rather the charged portion of the fatty acid carboxylates, and inside are our fatty acid tails, which exclude the water. But look what's right at the center of that micelle, a payload of oil and dirt, and the entire sphere of micelle gets dissolved, literally dissolved within the water. Okay, let's wrap this up. There are a number of other types of functional groups which we did not go over in any sort of detail at the beginning of this course, which do pop up from time to time, but they don't rise to the importance, say, of carboxylic acids or esters. But they can be said to be derived from carboxylic acids, the carboxylic acid derivatives, as I've shown here. As such, I have 4 of these types of structures to show you, and your task is only to be able to recognize these 4 structures when you see them. We're not going to go into nomenclature or reactions of these things, but they do have a place within organic chemistry synthesis or biochemistry, and we'll be seeing some of these structures down the road. So the first of these is known as an acid chloride. An acid chloride. So notice this has sort of it's derived from a carboxylic acid, but poking off from this carbonyl is a chloro group. That is something we've never seen. It is known as an acid chloride. Again, we're not going to go into this too much, but just enough to we'll see these occasionally just so you'll be able to recognize them. Another notable carboxylic acid derivative is called the acid anhydride, and this looks like we have sort of like 2 of these carboxylic acids perhaps connected together by an oxygen bridge. We might think of it in that manner. It looks very strange. It's known as an acid anhydride. Both the acid chloride and the acid anhydride are used frequently as reactive intermediates in organic synthetic design. Indeed, we'll look when we start looking at the synthesis of amides, another functional group, we will use one of these reactive intermediates in the formation of an amide. So these two are used typically in organic chemistry synthesis, and we see them occasionally. Two more carboxylic acid derivatives of note, which find more of their application in biochemistry, and indeed we'll be seeing these over and over. The first one is known as a thioester. Thioester. Thio typically means sulfur, and indeed we see a sulfur atom right in there. If this were an oxygen, not a sulfur at that point, this would be a traditional ester, a regular ester, but it's not. It is a sulfur atom, so this is known as a thioester. The question being, could you pick this out of a lineup? Lastly, a phosphoester, much more complex. We're going to be looking in detail at phosphoesters, particularly when we start talking about lipids and fats. But here we have sort of a strange, almost called a phosphocarbonyl, a P double bond O, connected to an oxygen, connected to a hydrocarbon-carbon. Some of these, we have some hydroxyls kicking off to the side on a phosphoester, very specific type of structure, but really the question only is, could you pick these out of a lineup? The thioester and the phosphoester types of structure are high energy bonds found in biochemical systems. We'll talk about what that term high energy means when we look into these a little deeper in the biochemistry portion, but we're not quite there yet.